Hello everyone, my name's Dr. Vile and welcome to my A-Level Chemistry YouTube channel. The purpose of this channel is all about getting you ready for your A-Level Chemistry exams. And with that in mind, we're going to focus on an A2 topic here from the WJC Chemistry, although this applies to pretty much every exam board. And we're going to be looking at what we mean by the rate equation. So in other words, the relationship between rate and concentration. So that's going to be the focus of the video. If you find it helpful, please remember to like, subscribe, share, and keep checking back for more content. So the general principle is that when you increase the concentration, the rate would increase. And we can see this from the diagram that's on the screen at the moment. On the left-hand side, you've got a small container and you've got 4 green particles and 4 red particles. And for the reaction to take place, there has to be a collision between the green and the red. They'd have to bounce into each other with enough energy to break the bonds and to make new bonds. And when there are only 4 particles in the container, which is a silly example, but just to illustrate it, the frequency of those collisions is going to be quite low. And therefore they're not going to collide as often, and therefore the rate of the reaction is going to be lower because there are less frequent collisions between the particles. Well, when we increase the concentration, we've kept the volume of the container the same, but we've got way more red and green particles in it. So hopefully you can see now that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 green particles and 9 or 10 red particles. And what that means is that the frequency of the collisions between the green and the red is going to increase. And therefore, if the frequency of the collisions increases, there is more probability of what we call a successful collision. And a successful collision is one in which there is energy of greater than the activation energy, and therefore enough energy to break the bonds. Now, changing the concentration doesn't change the energy of the collisions, it just changes the frequency of the collisions. And the more collisions there are, probability tells us that there is a higher chance of a successful collision. So that's the general principle. However, the actual relationship between rate and concentration is not always that straightforward, and that's what we're going to look at on the next slide, because there are a variety of different relationships between rate and concentration. That's what we're going to be investigating, this link between rate and concentration. And there are 3 relationships we need to know, and they are called orders of reaction. And I'll explain what that means as we go through. The first scenario is 0 order, and then you can have first order and second order. There are others, but at A level, that's all we need to worry about. First, second, and 0. So let's start about defining what we mean by that. 0 order is when there is no relationship between rate and concentration. So rate is unaffected by concentration. So when we have 0 order, the rate is unaffected by changes in concentration. So doubling the concentration would have absolutely no effect on rate. The second scenario is where we call first order. And first order means that rate is directly proportional to concentration. And what this means is, for instance, if we double the concentration, then the rate would double. If we treble the concentration, then the rate would treble, and so on. So when it's first order, we're looking for this directly proportional relationship. And the third scenario we need to encounter is second order. And this is perhaps the most complicated. And this is where rate is proportional to the square of the concentration. So rate is proportional to the concentration squared. So what I mean by that is if the concentration is doubled, then the rate would quadruple. Or if the concentration was times 3, then the rate would be times 9. And that's what we mean by second order. Rate is proportional to the concentration squared. So what we're going to try and do now is pull together this all into something called the rate equation. Now the rate equation takes into account these orders that we've just discussed. So imagine we've got a reaction between A and B going to products. The rate equation is always written out as follows. You always start with the word rate, which is the rate of the reaction, and that is equal to K. K is called your rate constant. And we're going to look at how to calculate that. And then that is times the concentration of A to the power of X. And the power of X simply means the order with respect to A. So it could be 0, could be 1, or could be 2. And then we times that by B to the power of Y, where X and Y are just the orders, so whether it's 0, 1, or 2. So let's define what we mean by that in a bit of writing. So K is your rate constant. The A in square brackets refers to the concentration of A. X is the order of the reaction with respect to A, sorry. The order with respect to A, and Y is the order with respect to B. And this is much easier if we look at a real example. So let's look at an actual question and try and work some stuff out. So here you've got the reaction between nitrogen dioxide and ozone producing N2O5 and oxygen. And what's happened here is that the reaction was carried out 3 times, experiment 1, experiment 2, and experiment 3. And the concentrations of the NO2 and the ozone were varied. So if you look at experiment 1 and compare it to experiment 2, hopefully you can see that the concentration of ozone is constant. It's staying the same. However, the concentration of the NO2 has gone from 0.00150 to 0.00225, and that means it's gone up by 1.5 times 1.5. And if you look at the rate, it's gone from 4.8 times 10 to the minus 8 to 7.2 times 10 to the minus 8. So that is also times 1.5. So increasing the concentration of the NO2 by times 1.5 makes the rate go up by 1.5. Therefore, it is first order with respect to the NO2. And I got that by looking at experiments 1 and 2. So whenever you do this, you need to find a pair of experiments where only one thing is changing and everything else is remaining constant, and then look and see how that influences the rate. So let's do it again now and try and do it for ozone. So I'm going to look at experiments 2 and 3. The concentration of the NO2 is constant, but hopefully you can see that the concentration of the ozone has doubled. And as a consequence, the rate has doubled. And if you're trying to work out how I worked out it's doubled, I took the bigger number, which is 1.44 times 10 to the minus 7, and I divided by the smallest number, 7.2 times 10 to the minus 8. And actually the bigger number is twice as big as the smaller number. So therefore it's also first order with respect to the ozone. Because doubling the concentration doubles the rate, it's directly proportional. And therefore our rate equation always starts with the word rate, is equal to K, our rate constant, times the concentration of the NO2. Now it's first order, so it's to the power of 1, times the concentration of the ozone to the power of 1. Now you might be sat there thinking something to the power of 1 just equals itself, and you are spot on if you're thinking that, and therefore if it's first order we don't actually need to bother putting to the power of 1 into our rate equation. We're just complicating things. But this is our rate equation. Now the question is most likely going to say calculate a value for the rate constant. So to do this we need to rearrange our equation to make K the subject. So you divide both sides by the concentration of NO2 and the concentration of ozone, and therefore K equals rate divided by the concentration of NO2 times the concentration of the ozone. And at this stage you need to plug some numbers in. Now you need to pick an experiment, any experiment, 1, 2 or 3. It doesn't actually matter because it's a rate constant, it will remain the same. The only way we change the rate constant is by changing temperature. So I'm just going to pick experiment 1 here, and I'm going to plug the numbers straight in. So the rate is 4.8 times 10 to the minus 8. And then you're dividing by the concentration of the NO2, which is 0.0015, times by the concentration of the ozone, which is 0.0025. And when you put that into the calculator, you get a value of 0.0128. It's not quite the final answer, I'm afraid, because we need to have units. And the units are relatively complicated. They're not the constant, we have to calculate them. So if we go back to this equation here, K equals rate divided by the concentration of the NO2 times the concentration of the ozone, and we substitute in the units. Well, the units of rate is moles per decimeter cubed per second, and then the units of concentration is moles per decimeter cubed, but there's 2 of them, so we have to write it out twice. That's technically the units, but we need to cancel it down, simplify it a little bit. The way to think about this is these moles here on the bottom are technically moles to the +1. When you bring them to the top, they become moles to the -1. So this mole here cancels with this mole here. The dm to the -3, bring it to the top, becomes dm to the +3, and it cancels out with this dm to the -3. Which leaves you with this that can't be cancelled down any further. So when you bring the mole to the +1 to the top of the equation, it becomes moles to the -1. dm to the -3, bring it to the top and it becomes dm to the +3. And then you're left with the s to the -1 that was there already. Okay, hopefully that was helpful, but let's look at another example. Here you've got the reaction between hydrogen and iodine, and you need to work out the rate equation and therefore the value for K, and therefore the units as well. So we're going to use the same logic. We've got 4 experiments and lots of different data. So let's just look at experiments 1 and 2 to start off with. Hopefully you can see there that the concentration of the iodine is constant, but that the concentration of the hydrogen has doubled, and as a consequence the rate doubles, and therefore it's first order with respect to the hydrogen. And now we need to find a pair of experiments where the hydrogen is constant, but the iodine changes. So what I'm going to do is focus in on experiments 2 and 4, because the concentration of the hydrogen is constant, but the concentration of the iodine has doubled. And as a consequence, the rate doubles, and therefore it's first order with respect to the iodine. So our rate equation is rate equals K times the concentration of the hydrogen times the concentration of the iodine. Rearrange to make K, so K equals rate divided by the concentration of the hydrogen times the concentration of the iodine. At this stage, plug some numbers in. Once again, it doesn't matter which experiment you go for as long as you're consistent, so don't pick and mix between the different experiments. Let's just go with experiment 1. And in experiment 1, we're going to use these numbers here. So the rate is 4.7 times 10 to the minus 6. And then you're dividing it by 0.01 times 0.01. And that comes out as 0.047. And the units, they're going to be the same as for the previous example actually. You've got moles per decimeter cubed per second on the top. And then you're dividing by moles per decimeter cubed twice on the bottom. So this can be cancelled down as before. And that leaves you with moles to the minus 1, dm to the plus 3, s to the minus 1. Okay, so we're going to look at a more complicated example now, just to finish. You've got the reaction of Fe3 plus with SN2 plus under acidic conditions. That's really important. It's under acidic conditions, which means that there are H plus ions present. You are given the pH in your table, so the first thing I would do is convert your pH into H plus. So it's the concentration of H plus. To do that, you get your Casio calculator, that's what I'm using, it might be different on your calculator, and I press shift, I press log, and then I press minus the pH. And that gives me a value of 1 when the pH is 0, and 0.1 when the pH is 1. So we're now ready to tackle the question. I am going to start by looking at experiments 3 and 4. So in experiments 3 and 4, the concentration of the Fe3 plus is constant. The concentration of the tin goes from 0.1 to 0.2. So that's doubled. And as a consequence, and the H plus is constant, the rate doubles. So it's first order with respect to the SN2 plus. So that's the easy bit of the question, I suppose. It's first order with respect to SN2 plus based on experiments 3 and 4. What about the Fe3 plus? Well, let's take this shading off and we'll have another look at some other experiments. If you look at experiments 1 and 2, the concentration of the SN2 plus is doubling. Now, because it's first order with respect to SN2 plus, we'd expect the rate to double. The Fe3 plus is times 1.5. The concentration of H plus is constant, and the rate is doubling. And that doubling comes about from the doubling of the SN2 plus, which means that increasing the Fe3 plus is having no additional effect on the rate, and therefore it must be zero order with respect to the Fe3 plus, because the 1.5 increase has no extra effect on the rate in addition to the times 2 from the SN2 plus. So it must be zero order. Zero order means it has no influence on the rate. So we're almost there. We want to work out now the order with respect to H plus. Well, because we said it's zero order with respect to Fe3 plus, we can ignore this now. We don't care about it. It's irrelevant. It has no influence on the rate at all. So I'm going to look at experiments 1 and 3. 1 and 3, where the concentration of the tin is constant and the concentration of the the H plus goes from 1 to 0.1. So that's dividing by 10, and as a consequence the rate goes down by 10 as well. So therefore it must be first order with respect to H plus. Okay, let's take the scribbles off and then we'll carry on. So we need to write our rate equation. We'd say that rate equals K times the concentration of the SN2 plus to the power of 1 times the concentration of the Fe3 plus to the power of 0 times the concentration of the H plus to the power of 1. Now this can be simplified. Something to the power of 1 just equals itself, so we can get rid of the power of 1. Something to the power of 0 just equals 1, and therefore it can actually disappear from the rate equation. So I can simplify the rate equation and say that rate equals K times the concentration of SN2 plus times the concentration of the H plus. And therefore K equals rate divided by the concentration of the SN2 plus times the concentration of the H plus. And at this stage, plug the numbers in. I'm just going to pick experiment 1. So that's these numbers here. Well, rate is 1.4 times 10 to the minus 2. The concentration of the SN2 plus is 0.1. And the concentration of the H plus is 1. Chuck that all into your calculator, and the answer comes out as 0.14, and that would have units of moles to the minus 1 dm cubed s to the minus 1. Same as for the previous ones. Okay. Anyway, I hope that was helpful. If you found this video helpful, please remember to like it, subscribe, keep checking back for more content, and I'll see you next time. Thanks everyone.